Hi, welcome back. This is section 8.6 on DeMoivre's theorem and powers and roots of complex numbers. Let's read through DeMoivre's theorem first, and then we can try some examples. DeMoivre's theorem says if r times the cosine of phi plus I sine phi is a complex number, and n is a real number, then r times the cosine of phi plus I sine phi, that complex number raised to the n power, is equal to r to the n times cosine of n times the angle phi plus I sine times the angle n phi. And in complex form, if we want to write it in the CIS form, we would simply have the complex number r CIS of phi raised to the n is equal to r to the n times CIS n phi. Now, I know sometimes we look at this number, this r cosine of phi plus I sine phi, and it looks really strange at first. And granted, if we're not used to seeing it like that, it can look strange. But what DeMoivre's theorem does for us is it makes the calculation so much easier than working in rectangular coordinates. So let's try an example. So here we go. There it is. We want to find 1 plus I root 3, that number raised to the 8th power, and write the answer in rectangular form. So the first thing I'd like to do is start with the 1 plus I root 3 and sketch this out where we think it would be. It's going to be in the first quadrant along the x, or we call the real axis now, the horizontal axis. Let me make that look more like an E. So along the real axis, it would be of length 1. And the y-axis would be of length root 3. And if we put a point up here in that corner, draw the line from, we can think of it as a position vector, from the origin out to that point. And then we're going to make a triangle here. Okay. So we know the two sides of the triangle. We also know that r is equal to 1 squared plus root 3 squared, and we'll take that square root. So we find that this is 1 plus 3, that's the radicand. We get square root of 4, which we know as 2. So we just found the hypotenuse of this right triangle, or we can think of it as the radius and circular function. So this is, in any case, that length of the position vector is of length 2. All right, let me just put this side of the triangle. This is root 3 on that side of the triangle. And we know this triangle, well, this angle we know is one of the special triangles. So we also know that this angle has to be 60 degrees from the length of the from the length of the sides, or we can call them the legs of the triangle. So let's move this down, make a little bit more room, and write this in this form here. So we have 1 plus I root 3 is equal to, we found the radius, or the modulus, as 2. And then in that CIS form, or the cosine plus I sine form, we would have the cosine of the angle, which we now know is 60 degrees, plus I times the sine of that same angle, 60 degrees. And that's what we have to this point. Now what we want to do is raise this number to the 8th power. So if I write 1 plus I root 3 to the 8th power, this we know as, I'm going to write the same thing I had on the line above. So I'm just going to put parentheses around it and raise both sides to the 8th power. So we have 2, and then cosine of 60 degrees plus I times sine of 60 degrees. And that is all raised to the 8th power. Now, DeMoivre's theorem says, if we go back and take a quick look at it, it says here that I can raise r to the n, so that's my 2 I can raise to the 8th power, and then these n's here I can just include as coefficients to the angle. So they're going to be 8s also. So let me erase these quickly, these marks I just made. And go back to the last screen. Find where we were. Okay, so we're going to have 2, and the marker, there we go. We're going to have 2 raised to the 8th power times the cosine of 8 times the angle, which is 60 degrees, plus I times the sine of 8 times 60 degrees, and close that parenthesis. 2 to the 8th, if we take 2 to the 8th power, we'll end up with 256. And cosine, instead of writing 8 times 60, we know that's going to be 480 degrees, plus I times the sine, that'll also be 480 degrees. But 480, that's larger than 360. So why don't we write this as the coterminal angle? If we just subtract out 360, we get 120 degrees, plus I times the sine of 120 degrees there. Okay, equals 256. And the cosine of 120, the sine of 120, if I just draw a little, let me draw this here, erase that first. Let me draw an angle, 120 degrees. We're going to be in the second quadrant. And this may be something you already know and you don't need to draw a triangle, but just in case. The cosine of 120, we know the horizontal axis, or this piece along the bottom of the triangle that I'm drawing in blue, that's going to have a length of a half. And since we're in the second quadrant, it'll be negative 1/2. And then this part, or the dotted line that I drew in red there, this has length √3 over 2, and we should know that angle is 120 degrees. And we can now finish this question. Instead of writing cosine of 120, we're going to write negative 1/2, plus I times the sine of 120, we're going to write √3 over 2. And just doing one other piece of simplification, if we multiply the 256 into both terms inside the parentheses, we will get a negative 128 and then a plus 128 I √3. Okay, so what we have here, the negative 128 plus 128 I √3 is the same number that we started with up here, the I plus I √3 to the 8th, and it's in rectangular form. Oh, I misread that. Hold on. Let me go back. It's not the same number that we started with. We started with 1 plus I √3, and then we raised that to the 8th power. And what we have here, we found 1 plus I √3. We wrote it in its polar form or trigonometric form, and then we've raised it to the 8th power using DeMoivre's theorem to end up with negative 128 plus 128 I √3. That's what we did. So let's try another example. And this one here, it says find √2 plus I √2, that number raised to the 5th power, and write answer in rectangular form. So I'm going to start again the same way that we started the last question here. And I'm going to graph this along the real axis, so the horizontal axis. It has a length of √2. And, well, it also, on the vertical axis, it has a length of √2. And that's the imaginary axis. So if we put a dot out there, and we draw a position vector to that dot, make a triangle. It's going to be a right triangle. So each of the legs of the triangle has length √2, and we should know what this is going to be already, but we'll go through the routine here. To find out the length of the modulus, or r, we're going to take √2 and square it, and then √2 and square this again, just the Pythagorean theorem, which equals, it's going to be 2 plus 2. We go to the square root of 4, which we end up with 2. So the modulus here again is 2. All right, we should recognize this angle in here. I'll call it phi, but we should recognize that phi is 45 degrees. It's one of our special triangles. So we can write this number here in this form, 2 times the cosine of 45 degrees plus I times the sine of 45 degrees. So now we're going to take that information that we just found and that way of writing the number and raise it to the 5th power. So let's start the same way, or continue the same way we did in the last example. We have root 2 plus I root 2. We're going to raise that number to the 5th power. So we know that we can write this number as 2 and then cosine 45 degrees plus I times the sine of 45 degrees, and that's going to be raised to the 5th power. Let's make some more room here. Now, applying DeMoivre's theorem, we're going to write this as 2 to the 5th times cosine of 5 times 45 degrees plus I times the sine of 5 times 45 degrees. Close the parentheses. Now, 2 to the 5th is 32. Then we're going to write cosine of 5 times 45 is going to give us 225. So that's plus I times the sine of 225, like that. And up until this point, right here, we have the trigonometric form of the answer, or polar form of our answer. But the directions tell us to take this to rectangular form. So let's continue. We're going to have 32 times the cosine of 225. We can draw a 225 degree angle here, and there's the reference angle, the reference triangle. So this is going to be negative root 2. This side will be negative root 2, and we know that this would be negative root 2 over 2 for the cosine. And then we have minus I times root 2 over 2. Just cleaning this up a little bit, multiplying the 32 into both of these terms inside the parentheses. We end up with a negative 16 root 2 and minus 16I root 2. And this is the rectangular form of the answer. Now, what we're going to do next is think about the roots, or experiment with the roots of complex numbers. We know that every non-zero complex number has exactly n distinct complex n roots. And DeMoivre's theorem can be extended to find all nth roots of a complex number. Okay, next we'll look at a definition of nth roots, and then the nth root theorem, and then apply this and try some examples. So here we have the definition. It says, for a positive integer n, the complex number a plus bi is an nth root of the complex number x plus yi if a plus bi to the n is equal to x plus yi. Going on to the theorem, the nth root theorem says if n is a positive integer, r is a positive real number, and phi is in degrees, then the non-zero complex number, r, times cosine phi plus I sine phi, has exactly n distinct nth roots given by the nth root of r times the cosine of alpha plus I sine alpha equals r to the 1 over n power times cosine of alpha plus I sine of alpha. Now alpha is equal to the angle phi over n plus 360 times k over n. K will start at 0 and go up through 1, 2, all the way to n minus 1. Let's try an example. All right. Find the 3 complex cube roots of negative 4 root 2 plus 4i root 2. So I'm going to start with negative 4 root 2 plus 4 times I and then root 2, and write this as 4 times negative root 2 plus I root 2. Now I'm going to continue and factor this out. I'm going to keep factoring out maybe another 2. So let's write this as 8, and then in parentheses, negative root 2 over 2 plus I root 2 over 2. Now once it's in this form, we know that we can write this as 8 cosine of 135 degrees plus I times the sine of 135 degrees. Now what I did here, I kept factoring out numbers, meaning the 4 right here and then the 8, until inside the parentheses, I got the coordinates of a point on the unit circle. And that point, if I think about it, and I'm going to erase this, but let me just write this, negative root 2 over 2 root 2 over 2. That puts me in the second quadrant of that point, and it gives me a 45-degree reference angle. And this larger angle in standard position is 135 degrees. That's how I get the 135 and the 135 degrees right here. The 8, it happens to be the modulus. So there's longer ways or shorter ways to find this information. But I was interested in finding the modulus, the 8, and what these numbers were, the angle numbers, 135. So let me erase some of this stuff here, these arrows, and then we'll continue. If you're more comfortable finding this modulus information, the angle information in another way, that's fine too. But in any case, we have the modulus 8, the angle is 135 degrees, and we started out with the rectangular form here and ended up with the trigonometric, or we can call it the polar form, trigonometric form right here. Now, in the definition or the theorem on the previous screen, it has this k. It's equal to 0, k is equal to 1, and so forth. How do I know what I'm going to start with? We're always going to start with 1. We're always going to start with 0 as the first number that we work with, and then we'll go to 1 and 2 up until whatever we need. So k is going to be 0. We know that. And I need 3 of these because I have 3 complex cube roots. So k is equal to 0, k is equal to 1, k is equal to 2. That's what we're going to start with there. And we're going to apply DeMoivre's theorem when k is equal to 0. We'll start here. And what we get here is 8 times the cosine of 135 degrees plus I times the sine of 135 degrees. And then we'll close that parenthesis twice and raise that. Notice we want cube roots, which we're going to write as the 1/3 power. Now, equals, DeMoivre's theorem, when we apply this, will be 8 to the 1/3 power times the cosine. And I'm looking back here and on the theorem that we're going to work with. And the angle here, I'm looking at where alpha is phi over n plus 360k divided by n and so forth. So we have to write the cosine, and it's the cube root, so we're going to write the 1/3 times 135 degrees. And let's do that. Plus I times the sine of 1/3 times 135 degrees. Multiplying this out, 8 to the 1/3 power is just 2. And then the cosine of 135 divided by 3 is 45 degrees. Plus I sine, this is also going to be 45 degrees. So we can, that's our k is equal to 0. Make some more room here, and then we're going to find when k is equal to 1. Here we have 8 times the cosine of 135 degrees plus I sine 135 degrees. Again, we're going to raise this to the 1/3 power equals 8 to the 1/3 times cosine of 1/3 times 135 degrees plus 360 degrees over 3 plus I times the sine of 1/3 times 135 degrees plus 360 degrees over 3. Cleaning this up, we have 8 to the 1/3 is 2 again. I'm making some more room, so we get the cosine of 45 degrees. That's 135 degrees over 3. That's still 45 degrees. And then 360 degrees, this new part for k is equal to 1. We have 360 over 3, which is 120 degrees. Plus I times the sine, we're going to get 45 degrees again, plus 120 degrees again. Close the parenthesis twice. So we get 2 is equal to the cosine. 45 and 120 is 165 degrees, plus I times the sine of 165 degrees. Let me make that look like a 5. 165 degrees. All right, so let's go to k is equal to 2. Make some more room. Now we start the same way, 8, and then cosine 135 degrees plus I times the sine of 135 degrees. Close the parenthesis. We're taking that to the 1/3 power again. Now when k is equal to 2, we're going to get 8 to the 1/3 times the cosine of 1/3 times 135 degrees plus, and the k's I haven't been writing before when k was 0 or k was 2 in the formula, but let me show you. I'm going to write, since k is 2 this time, we're going to have 360 degrees. The k is 2. When k was 0, this whole term, the second term, didn't drop down and we didn't write it. When k was 1, we just wrote 360, not 360 times 1, and that's going to be over 3. And then we have plus I times the sine of the same argument, 1/3 times 135 degrees plus 360 degrees times 2 over 3. And close the parenthesis again. Cleaning this up, we have 2, 8 to the 1/3 is 2, times the cosine, this is still 45 degrees, plus 360 times 2 divided by 3 is 240, plus I times the sine of 45 plus 240, which equals 2 times the cosine, that's going to be 285, plus I times the sine of 285 degrees. So we were asked to find the 3 complex cube roots of that given number. All right, so here was one. Let's see, when k is 1, here's another one. When k is equal to 2, we get this number right here. All right, in this example, we want to find all 4th roots of -8 plus 8I root 3. And we want to write the roots in rectangular form. So let's start with -8 plus 8I root 3. And write this as, let's see, we'll factor out an 8. And we're left with a -1 plus I root 3. And I'm going to continue. I'm going to factor out, let's see, another factor of 8. So why don't we say another factor of 2? That would be 16. And inside the parentheses, I have -1/2 plus I root 3 over 2. Now, inside the parentheses, you can see that I have, let's see, -1/2 and root 3 over 2. If we think about plotting that point, that's going to put us in the second quadrant. And let's see, it's going to be that point right there. -1/2 root 3 over 2. So when I have these coordinates of a point on the unit circle, my 16 is my modulus, and my angle, this angle here would have to be 120 degrees. So let me erase that arrow, and then we'll continue. So, oops, erase it all. This is equal to 16 times the cosine of 120 degrees plus I times the sine of 120 degrees. All right, so we started out in rectangular form. Now we have this in trigonometric or polar form. And we are going to let k start at 0. It's going to go to 1, 2, and then 3. So I have 4 roots here, or 4 k values, 0, 1, 2, and 3, because we have 4 roots here. So there's the 4 values that we're going to use to get the roots. We're going to apply DeMoivre's theorem, which is the nth root theorem. So for k being equal to 0, let's see, we have 16 times the cosine of 120 degrees plus I times the sine of 120 degrees. That's raised to the 1/4 power. So let's write this out as, whoops, I jumped ahead there. We're going to write this first as 16 to the 1/4 power, which is 2, and then times the cosine of, let's write this as 120 over 4 plus, we're going to take 360 degrees times 0, that's our k, the 0, over 4. Okay, when we do that, this term drops out to be 0 anyway, plus I times the sine of 120 degrees over 4 plus 360 degrees times 0 over 4. This piece drops out because it's 0. And continuing here, let's make some more room. The 1/4 power of 16 is 2. And then we have the cosine. 120 over 4 plus 0 is 30 degrees. Plus I times the sine of 30 degrees. This is equal to 2 times, the cosine of 30 is going to give us root 3 over 2, plus I times the sine of 30 is 1/2. And we can write this as, I'm going to work this way across the board here of the screen, root 3 plus I. So there's one of our roots there. Let's go on. That was k equals 0. Let's try k is equal to 1. Starting the same way, we have 16 and then times the cosine 120 degrees plus I times the sine of 120 degrees. All that raised to the 1/4 power. Okay, that's going to be equal to 16 to the 1/4 power times cosine of 120 degrees over 4 plus 360 degrees times k. This time k is 1 over 4. Plus I times the sine of 120 degrees over 4 plus 360 degrees times 1 over 4. So 16 to the 1/4 power is 2. And then the cosine of 120 over 4, that's going to give us 30 again. Let me put that in. Plus 360 over 4 is 90. Plus I times the sine of 30 degrees plus 90 degrees. And finally, we get 2 times the cosine. This is 120 degrees plus I sine of 120 degrees, which equals -1 plus I root 3. Okay, there's one of our answers. Let's make some more room. So this is for when k is 2. We have 2 more of these to go. Sure you can see what's happening here. We have 16 times the cosine of 120 degrees plus I sine of 120 degrees, parenthesis, parenthesis to the 1/4 power. This is equal to 2 times cosine 120 over 4. So it's always 120 over 4, and then it's plus a multiple, say, of 360 over 4. This is going to be plus, or times, excuse me. Let's make this a times symbol right here. Times k, which is 2 over 4, plus I times the sine of 120 degrees over 4 plus 360 degrees times 2, which is 2 is the k, over 4. All right, so this is 2 times cosine. 120 over 4 is 30 degrees, plus 360 times 2 over 4 is 180 degrees, plus I sine of 30 plus 180 degrees. We end up with here 2 times the cosine of 210 degrees plus I times the sine of 210 degrees equals, let's see, equals 2. The cosine of 210 is negative root 3 over 2 minus I times the sine of 210 is 1/2 equals negative root 3 minus I. So there's another answer. We'll extend the page one more time because we have one more k value. We have to do the same thing, this time when k is equal to 3. So we start the same way that we have been, 16 times the cosine of 120 degrees plus I times the sine of 120 degrees to the 1/4 power equals 16 to the 1/4 times the cosine of, we'll write this as 120 degrees over 4 plus 360 degrees times k. K is 3, and that's over 4, plus I times the sine of 120 degrees over 4 plus 360 degrees times 3, which is k, over 4. So we get 2 times the cosine of 30 plus, that's going to be 270, plus I times the sine of 30 plus 270 equals 2 times cosine of, that's going to be 300 degrees, plus I times the sine of 300 degrees. Almost done. So we get the cosine of 300 is 1/2 minus I times the sine of 300 is root 3 over 2. So multiplying the 2, and we get 1 minus I root 3. There we go. Okay, so let's go on and talk about solving equations. Now, in this example, we want to find all complex number solutions, meaning roots, of this equation x cubed minus 8 equals 0 in trigonometric form, and graph solutions as vectors in the complex plane. So this is how we can solve this equation. I'm going to start with x cubed minus 8 equals 0. That's given to us. And I'm going to start by putting the 8 on the other side. So we have x cubed equals 8. And let me just move this and make some more room here. So x cubed is equal to 8. And we can write this as x cubed is equal to, well, that number 8, we could write it, it's a It's a real number, 8, but it's also a complex number. And we can see that it's a complex number by writing it as 8 plus 0i, which we can write x cubed as, factoring out an 8, we get a 1 plus 0i, which we can continue and write x cubed is equal to 8 times the cosine, I'm putting it in the CIS form, the cosine of 0 degrees plus I times the sine of 0 degrees. Okay. At this point, let's take the cube root of both sides. So the cube root of the left side is simply x. The cube root of the right side, we know we can write this as 8 times the cosine of 0 degrees plus I sine 0 degrees, close two sets of parentheses, and raised to the 1/3 power. Now, at this point, I know I can write 8 to the 1/3 times the cosine of 1/3 times 0 degrees plus I sine of 1/3 times 0 degrees. Make some more room. And 8 to the 1/3, well, we know is 2. So this gives us the cosine of 1/3 times 0 is still 0 degrees plus I times the sine of 0 degrees equals 2 times the cosine of 0 is 1 plus I times the sine of 0 is 0. And this ends up being just 2. So 2 is the real number solution. I know we all knew that, 2 cubed is 8 before we came into this class, but there's 2 other solutions, and this would be the example when k is equal to 0. Let's try k being equal to 1 and see what happens. We get x is equal to 8 to the 1/3 power times the cosine of 1/3 times 0 degrees plus 360 times a multiple of k, well, it's just times 1 because k is 1, over 3, plus I times the sine of 1/3 times 0 degrees plus 360 times k times 1. Let me make it look more like times 1, 360 degrees times 1 over 3. And then 2 to the 1/3 is, or 8 to the 1/3 is 2, excuse me. And this gives us cosine of 120 degrees plus I sine of 120 degrees equals 2 times the cosine of 120 is negative 1/2 plus I times the sine of 120 is root 3 over 2. So this ends up being negative 1 plus I root 3. Okay, so there's our second answer. Here's our first one that we found that was just a 2. And then we have negative 1 plus I root 3. And we have one more to find. So that's when k is equal to 2. So let's try this again. X is equal to 8 to the 1/3 power times the cosine of 1/3 times 0 plus 360 degrees times k, which is 2 this time, over 3, plus I times the sine of 1/3 times 0 degrees plus 360 times k, which is 2, over 3. Close the parenthesis twice. 8 to the 1/3 is 2. That leaves us with the cosine of, it's going to be 240, plus I sine 240 equals 2 times the cosine of 240 is 1/2, but negative, minus I root 3 over 2. This ends up being negative 1 minus I root 3. All right. And that makes sense because we know these Solutions have to come in complex conjugate pairs. So we have negative 1 plus I root 3, and we just found negative 1 minus I root 3. So if we were to write the solution set, we could write it, let's see, how about just writing it as CIS of 0 degrees, CIS 120 degrees, CIS of 240 degrees. And we also want to graph this. To graph the solutions in the complex plane. Complex. All right. All right. So here's our real axis. Here's our imaginary axis. And I'll graph these in a different color. How about red? And I'm going to go back up and graph 2. The first answer that we found was 2. So if I draw this vector, okay, and that's 2 along the real axis. So there's one solution, and we could write this as 2 times the cosine, and that's of 0 degrees, plus I times the sine of 0 degrees. Now the next vector we have is at angle 120 degrees. So this answer would be 2 times the cosine of 120 degrees plus I sine of 120 degrees. And 240. So 240, there's the vector at 240 degrees, and we can write this as 2 times the cosine of 240 degrees plus I times the sine of 240 degrees. And they are the 3 solutions. They're equally spaced around the complex plane. Okay, I have another example here. We want to find all solutions, meaning roots of x to the 4th minus I equals 0, and we want to graph the solutions. So if we start out with x to the 4th minus I equals 0, and I'm going to start this one the same way we did the last example. X to the 4th equals I. So that means x to the 4th is equal to, now this complex number, I could write it in the a plus bi form, meaning 0 plus I. Then we have x to the 4th, which is equal to, now this would correspond to the cosine of 90 is 0 in the CIS form, plus I times the sine of 90, because the sine of 90 is 1. So if we, let's see, we'll take the 4th root of each side, so this gives us x, and that would give us the cosine of 1/4 times 90 degrees, plus I times the sine of 1/4 times 90 degrees. So x is equal to, the cosine of 90 divided by 4 is 22.5 degrees, plus I times the sine of 22.5 degrees. All right, and that corresponds to when k is equal to 0. Let's try k is equal to 1. We have x is equal to the cosine of 22.5, I'll just use that instead of 90 over 4, plus multiple of 360, so 360 times 1, because k is 1 this time, and over 4, plus I times the sine of 22.5 degrees, plus the 360 times 1 over 4, close the parenthesis twice. No, one too many times. Let's close the parenthesis once. and clean this up. So we get x is equal to the cosine of 360 over 4 plus 2 is 22, 112. So it's going to be 112 and a half degrees plus I times the sine of the same 112 and a half degrees. Okay, let me just move this down a bit. This here, k is equal to 1. Get rid of all those marks. So there's when k is equal to 1. Let's try k equal to 2. I'm going to make some more room here. Whoa. So for k equal to 2, we have x is equal to the cosine, 22.5 again, plus 360 degrees times k, which is 2 over 4, plus I times the sine of 22.5 degrees, plus 360 degrees times 2 over 4 equals cosine 22.5 degrees plus 180 degrees plus I times the sine of 22.5 plus 180 degrees. So we get the cosine of 202.5 degrees plus I sine of the same 202.5 degrees. So that's when k is equal to 2. Ooh, whoops. There we go. Now we have one more when k is equal to 3. So we have x is equal to cosine 22.5 degrees plus 360 degrees times 3 over 4 plus I times the sine of 22.5 degrees plus 360 degrees times 3 over 4. All right. So we add all these up and we're going to find that we get the cosine of 292.5 degrees plus I times the sine of 292.5 degrees, and that is when k is 3. So we can think of the solution set. Let's see. I'll put it in the CIS form. We have 22.5 degrees. Then CIS 112.5 degrees. CIS 202.5. And then the last one was 292. So CIS 292.5 degrees. And there we go. So we're also asked to graph this. So let's graph the solutions. So we just draw our coordinate system, put a circle here, and I'll graph these in red again. We notice that the first angle is 22.5. So in standard position, let's see, an angle that's about 22.5 would look like this. So this would be CIS 22.5 degrees. And then 112.5 degrees would put us up about here. So that's CIS 112.5 degrees. And then 202 would put us here. So that's CIS of 202.5 degrees. And then we have one more, which is 292. So CIS 292.5 degrees. And that is the graph of our solutions. So that concludes this video for section 8.6 on DeMoivre's theorem. Thank you, and I will see you next time. Thanks. Bye.